An ice age is a period of long-term reduction in the temperature of Earth's surface and atmosphere, resulting in the presence or expansion of continental and polar ice sheets and alpine glaciers. Within a long-term ice age, individual pulses of cold climate are termed glacial periods, and intermittent warm periods are called interglacials. Glaciologically, ice age implies the presence of extensive ice sheets in the northern and southern hemispheres. By this definition, we are in an interglacial period, the Holocene, of the ice age that began 2.6 million years ago at the start of the Pleistocene epoch, because the Greenland, Arctic, and Antarctic ice sheets still exist. Origin of Ice Age theory. In 1742, Pierre Martel, an engineer and geographer living in Geneva, visited the valley of Chamonix in the Alps of Savoy. 2 years later he published an account of his journey. He reported that the inhabitants of that valley attributed the dispersal of erratic boulders to the glaciers, saying that they had once extended much farther. Later similar explanations were reported from other regions of the Alps. In 1815 the carpenter and chamois hunter Jean-Pierre Pérodin explained erratic boulders in the Val de Bains in the Swiss canton of Valais as being due to glaciers previously extending further. An unknown woodcutter from Maringen in the Bernese Oberland advocated a similar idea in a discussion with the Swiss-German geologist Jean de Charpentier in 1834. Comparable explanations are also known from the Val de Ferride in the Valais and the Seeland in western Switzerland and in Goethe's scientific work. Such explanations could also be found in other parts of the world. When the Bavarian naturalist Ernst von Bibra visited the Chilean Andes in 1849 to 1850, the natives attributed fossil moraines to the former action of glaciers. Meanwhile, European scholars had begun to wonder what had caused the dispersal of erratic material. For the middle of the 18th century, some discussed ice as a means of transport. The Swedish mining expert Daniel Tylers was, in 1742, the first person to suggest drifting sea ice in order to explain the presence of erratic boulders in the Scandinavian and Baltic regions. In 1795, the Scottish philosopher and gentleman naturalist James Hutton explained erratic boulders in the Alps by the action of glaciers. 2 decades later, in 1818, the Swedish botanist Göran Wallenberg published his theory of a glaciation of the Scandinavian peninsula. He regarded glaciation as a regional phenomenon. Only a few years later, the Danish-Norwegian geologist Jens Esmark argued a sequence of worldwide ice ages. In a paper published in 1824, Esmark proposed changes in climate as the cause of those glaciations. He attempted to show that they originated from changes in Earth's orbit. During the following years, Esmark's ideas were discussed and taken over in parts by Swedish, Scottish and German scientists. At the University of Edinburgh, Robert Jameson seemed to be relatively open to Esmark's ideas. As reviewed by Norwegian professor of glaciology Bjorn G. Anderson, Jameson's remarks about ancient glaciers in Scotland were most probably prompted by Esmark. In Germany, Albrecht Reinhard Bernhardi, a geologist and professor of forestry at an academy in Dreißigacker, since incorporated in the southern Thuringian city of Meiningen, adopted Esmark's theory. In a paper published in 1832, Bernhardi speculated about former polar ice caps reaching as far as the temperate zones of the globe. In 1829, independently of these debates, the Swiss civil engineer Ignaz Venet explained the dispersal of erratic boulders in the Alps, the nearby Jura Mountains, and the North German plain as being due to huge glaciers. When he read his paper before the Schweizerische Nachforschende Gesellschaft, most scientists remained skeptical. Finally, Venet convinced his his friend Jean de Charpentier. De Charpentier transformed Venet's idea into a theory with a glaciation limited to the Alps. His thoughts resembled Wallenberg's theory. In fact, both men shared the same volcanistic, or in de Charpentier's case rather Plutonistic assumptions, about the Earth's history. In 1834, de Charpentier presented his paper before the Schweizerischen Forschungsgesellschaft. In the meantime, the German botanist Carl Friedrich Schimper was studying mosses which were growing on erratic boulders in the alpine upland of Bavaria. He began to wonder where such masses of stone had come from. During the summer of 1835 he made some excursions to the Bavarian Alps. Schimper came to the conclusion that ice must have been the means of transport for the boulders in the alpine upland. In the winter of 1835 to 1836 he held some lectures in Munich. Schimper then assumed that there must have been global times of obliteration with a cold climate and frozen water. Schimper spent the summer months of 1836 at Devens, near Bex, in the Swiss Alps with his former university friend Louis Agassiz and Jean de Charpentier. Schimper, de Charpentier and possibly Venetz convinced Agassiz that there had been a time of glaciation. During winter 1836, Agassiz and Schimper developed the theory of a sequence of glaciations. They mainly drew upon the preceding works of Venetz, de Charpentier and on their own fieldwork. Agassiz appears to have been already familiar with Bernhard's paper at the time. At the beginning of 1837, Schimper coined the term Ice Age for the period of the glaciers. In July 1837, Agassiz presented the synthesis before the annual meeting of the Schweizerischen Forschungsgesellschaft at Neuchâtel. The audience was very critical and some opposed to the new theory because it contradicted the established opinions on climatic history. Most contemporary scientists thought that the Earth had been gradually cooling down since its birth as a molten globe. In order to overcome this rejection, Agassiz embarked on geological fieldwork. He published his book Study on Glaciers in 1840. De Charpentier was put out by this, as he had also been preparing a book about the glaciation of the Alps. De Charpentier felt that Agassiz should have given him precedence as it was he who had introduced Agassiz to in-depth glacial research. Besides that, Agassiz had, as a result of personal quarrels, omitted any mention of Schimper in his book. Altogether, it took several decades until the Ice Age theory was fully accepted by scientists. This happened on an international scale in the second half of the 1870s following the work of James Croll, including the publication of Climate and Time in the Geological Relations in 1875, which provided a credible explanation for the causes of ice ages. Evidence for ice ages. There are three main types of evidence for ice ages: geological, chemical, and paleontological. Geological evidence for ice ages comes in various forms, including rock scouring and scratching, glacial moraines, drumlins, valley cutting, and a deposition of tilatilites and glacial erratics. Successive glaciations tend to distort and erase the geological evidence, making it difficult to interpret. Furthermore, this evidence was difficult to date exactly. Early theories assumed that the glacials were short compared to the long interglacials. The advent of sediment and ice cores revealed the true situation: glacials are long, interglacials short. It took some time for the current theory to be worked out. The chemical evidence mainly consists of variations in the ratios of isotopes in fossils present in sediments and sedimentary sedimentary rocks and ocean sediment cores. For the most recent glacial periods, ice cores provide climate proxies from their ice, and atmospheric samples from included bubbles of air. Because water containing heavier isotopes has a higher heat of evaporation, its proportion decreases with colder conditions. This allows a temperature record to be constructed. However, this evidence can be confounded by other factors recorded by isotope ratios. The paleontological evidence consists of changes in the geographical distribution of fossils. During a glacial period, cold-adapted organisms spread into lower latitudes, and organisms that prefer warmer conditions become extinct or are squeezed into lower latitudes. This evidence is also difficult to interpret because it requires sequences of sediments covering a long period of time, over a wide range of latitudes, and which are easily correlated. Ancient organisms which survive for several million years without change and whose temperature preferences are easily diagnosed, and the finding of the relevant fossils. Despite the difficulties, analysis of ice core and ocean sediment cores has shown periods of glacials and interglacials over the past few million years. These also confirm the linkage between ice ages and continental crust phenomena such as glacial moraines, drumlins, and glacial erratics. Hence, the continental crust phenomena are accepted as good evidence of earlier ice ages when they are found in layers created much earlier than the time range for which ice cores and ocean sediment cores are available. Major ice ages. There have been at least 5 major ice ages in the Earth's past. Outside these ages, the Earth seems to have been ice-free even in high latitudes. Rocks from the earliest well-established ice age, called the Huronian, formed around 2.4 to 2.1 Ga ago during the early Proterozoic Eon. Several hundreds of km of the Huronian supergroup are exposed 10 to 100 kilometers north of the north shore of Lake Huron, extending from near Sault Ste. Marie to Sudbury, northeast of Lake Huron, with giant layers of now lithified till beds, dropstones, varves, outwash, and scoured basement rocks. Correlative Huronian deposits have been found near Marquette, Michigan, and correlation has been made with Paleoproterozoic glacial deposits from Western Australia. The next well-documented ice age, and probably the most severe of the last billion years, occurred from 850 to 630 million years ago and may have produced a snowball Earth in which glacial ice sheets reached the equator, possibly being ended by the accumulation of greenhouse gases such as CO2 produced by volcanoes. The presence of ice on the continents and pack ice on the oceans would inhibit both silicate weathering and photosynthesis, which are the two major sinks for CO2 at present. Quote, "It has been suggested that the end of this ice age was responsible for the subsequent Ediacaran and Cambrian explosion. Though this model is recent and controversial, the Andean Saharan occurred from 460 to 420 million years ago, during the late Ordovician and the Silurian period. The evolution of land plants at the onset of the Devonian period caused a long-term increase in planetary oxygen levels and reduction of CO2 levels, which resulted in the Karoo Ice Age. It is named after the glacial tills found in the Karoo region of South Africa, where evidence for this ice age was first clearly identified. There were extensive polar ice caps at intervals from 360 to 260 million years ago in South Africa during the Carboniferous and early Permian periods. Correlatives are known from Argentina, also in the center of the ancient supercontinent Gondwana. The current ice age, the Pliocene Quaternary glaciation, started about 2.58 million years ago during the late Pliocene, when the spread of ice sheets in the northern hemisphere began. Since then, the world has seen cycles of glaciation with ice sheets advancing and retreating on 40,000 and 100,000 year timescales called glacial periods. Glacials are glacial advances, and interglacial periods. Interglacials are glacial retreats. The Earth is currently in an interglacial, and the last glacial period ended about 10,000 years ago. All that remains of the continental ice sheets of the Greenland and Antarctic ice sheets and smaller glaciers such as on Baffin Island. Ice ages can be further divided by location and time. For example, the names RISs and WURM refer specifically to glaciation in the alpine region. The maximum extent of the ice is not maintained for the full interval. The scouring action of each glaciation tends to remove most of the evidence of prior ice sheets almost completely, except in regions where the later sheet does not achieve full coverage. Evidence of a recent extreme ice age on Mars was published by the journal Science in 2016. Just 370,000 years ago, the planet would have appeared more white than red. Glacials and interglacials. Within the ice ages, more temperate and more severe periods occur. The colder periods are called glacial periods. The warmer periods interglacials, such as the Eemian stage. Glacials are characterized by cooler and drier climates over most of the Earth and large land and sea ice masses extending outward from the poles. Mountain glaciers in otherwise unglaciated areas extend to lower elevations due to a lower snow line. Sea levels drop due to the removal of large volumes of water above sea level in the ice caps. There is evidence that ocean circulation patterns are disrupted by glaciations. Since the Earth has significant continental glaciation in the Arctic and Antarctic, we are currently in a glacial minimum of a glaciation. Such a period between glacial maxima is known as an interglacial. The glacials and interglacials also coincided with changes in Earth's orbit called Milankovitch cycles. The Earth has been in an interglacial period known as the Holocene for more than 11,000 years. It was conventional wisdom that the typical interglacial period lasts about 12,000 years, but this has been called into question recently. For example, an article in Nature argues that the current interglacial might be most analogous to a previous interglacial that lasted 28,000 years. Predicted changes in orbital forcing suggest that the next glacial period would begin at least 50,000 years from now, even in absence of human-made global warming. Moreover, anthropogenic forcing from increased greenhouse gases might outweigh orbital forcing for as long as intensive use of fossil fuels continues. Positive and negative feedback in glacial periods. Each glacial period is subject to positive feedback which makes it more severe, and negative feedback which mitigates and eventually ends it. Positive feedback processes ice and snow increase Earth's albedo, i.e., they make it reflect more of the sun's energy and absorb less. Hence, when the air temperature decreases, ice and snow fields grow, and this continues until competition with a negative feedback mechanism forces the system to an equilibrium. Also, the reduction in forests caused by the ICE's expansion increases albedo. Another theory proposed by Ewing and Don in 1956 hypothesized that an ice-free Arctic Ocean leads to increased snowfall at high latitudes. When low-temperature ice covers the Arctic Ocean, there is little evaporation or sublimation, and the polar regions are quite dry in terms of precipitation, comparable to the amount found in mid-latitude deserts. This low precipitation allows high-latitude snowfalls to melt during the summer. An ice-free Arctic Ocean absorbs solar radiation during the long summer days, and evaporates more water into the Arctic atmosphere. With high precipitation, portions of the snow may not melt during the summer, and so glacial ice can form at lower altitudes and more southerly latitudes, reducing the temperatures over land by increased albedo as noted above. Furthermore, under this hypothesis, the lack of oceanic pack ice allows increased exchange of waters between the Arctic and the North Atlantic Oceans, warming the Arctic and cooling the North Atlantic. Additional fresh water flowing into the North Atlantic during a warming cycle may also reduce the global ocean water circulation. Such a reduction would have a cooling effect on northern Europe, which in turn would lead to increased low-latitude snow retention during the summer. It has also been suggested that during an extensive glacial, glaciers may move through the Gulf of St. Lawrence, extending into the North Atlantic Ocean far enough to block the Gulf Stream. Negative feedback processes. Ice sheets that form during glaciations cause erosion of the land beneath them. After some time, this will reduce land above sea level and thus diminish the amount of space on which ice sheets can form. This mitigates the albedo feedback, as does the lowering in sea level that accompanies the formation of ice sheets. Another factor is the increased aridity occurring with glacial maxima, which reduces the precipitation available to maintain glaciation. The glacial retreat induced by this or any other process can be amplified by similar inverse positive feedbacks as for glacial advances. According to research published in Nature Geoscience, human emissions of carbon dioxide will defer the next ice age. Researchers used data on Earth's orbit to find the historical warm interglacial period that looks most like the current one, and from this have predicted that the next ice age would usually begin within 1,500 years. They go on to say that emissions have been so high that it will not